for that stuff.
Yeah, we got that equation from this stuff, just solving for Rx instead of VI.
Okay.
So we'll get a number here and then I'll try to connect it. It looks like Cloud of Faith again is being placed in Giovanni.
2,949.6.
2,900
49.6.
units.
Meters per second squared,
No, it's not an acceleration,
it's just meters per second.
Meters.
just meters.
Oh,
It's a distance, it's a radius. All right, so if I took our sun and using my godlike powers, shrank it down so that the radius was underneath 2,949.6 meters, that even something traveling the speed of light cannot escape. If the planet is, or the sun is larger than that, then there are things that can escape. So if I have a star, so if our sun shrank down to, let's say, 4,000 meter radius, then it will not, then light could still escape and get to us. Now, the escape speed would be incredibly hard, so light traveling at the speed of light could make it. Smaller things potentially could not. So if I have an object, so I take our sun, I shrink it down, so we're talking, so if the diameter would be roughly double that, so as a crude estimate, Peters Creek Parkway to Haines Mall. So if the sun shrank down into that size space without losing any mass, it would be a black hole because nothing could escape it. The Schwarzschild radius is the radius of a black hole. So, will our sun become a black hole at some point?
yeah.
When you look at stars, the process of a star, according to Orkard theory, we got two major forces involved here, two major things. There's a lot of mass, so it's pulling on itself. There's a gravitational pull trying to compress the whole thing. Meanwhile, there's a constant release of energy. It turns out, if I take two hydrogens and smash them together with enough energy, I'll create a helium plus energy that will escape. If I take two heliums and smash them together, I will get a beryllium plus some energy. Not as much as two hydrogens. And so forth, up until, I think it's lead. There's Pb. Oh, Pb's down there. Actually, I was thinking it was somewhere here. It might be iron. Anything, any of the elements below that, if I smash them together, I'm going to create something that has less mass, and that loss of mass will go into energy that's released in the form of either it'll go into a small particle with its kinetic energy, or it'll go into radiation or something. Anything above that on the periodic table, in order to get the excess energy, I need to break it apart. So uranium is the largest of the natural elements, which is down there at 92 at the bottom. So from anything from, assuming it's iron up to uranium, I have to split it apart. Now uranium is going to give you the most bang for the buck in terms of splitting it apart, in terms of fission. Hydrogen is going to give the biggest bang for the buck when you slam stuff together. Matter of fact, slamming two hydrogens gets more energy than splitting a uranium. Splitting the uranium in order to get energy released, that's the atomic bomb. Smashing two hydrogens together, the hydrogen bomb. The way our hydrogen bombs are created right now, it's really difficult to smash two hydrogens together. So you need a lot of energy. Now, in theory, a hydrogen bomb doesn't give off the harmful radiation like the atomic bomb does. However, in order to get enough energy to smash them together in the hydrogen bomb, we have an atomic bomb in there. So the radiation comes from basically the detonator to get the hydrogens to smash into each other. So, bunch of hydrogen burning up, colliding, there's a lot of energy there, they'll collide, create some helium, release energy. And so there's this, what's generally referred to as radiation pressure, there's radiation working its way out. And so right now our sun's it seems to have a nice balance between the gravitational pull on itself and the radiation coming out. At some point, the hydrogen is going to run out, in which case we'll start burning off the helium. There's the less mass, so the pull gets smaller and becomes less and less, but we're also having less radiation pressure, and it becomes a balance between those two. Based on the current theories, our sun, eventually the loss of energy / the loss of mass is going to be faster than the loss of radiation, and our sun should get bigger at some point. I've heard various people say eventually the sun will engulf the earth. That is not actually going to happen. Because as the sun gets less massive, there's less pull on Earth or less warping of space, and Earth is going to move farther out. So eventually the sun will be here, but the Earth won't be. And we as a species will be long gone by then anyway. Either long gone from the universe or long gone from Earth. So how do you get the black hole or the supernova or anything like that? Well, when you run out of the energy and suddenly, or enough of the energy, and suddenly, if you have a very quick loss of radiation pressure, suddenly you have a lot of gravitational pull, the thing's going to collapse in on itself. If it collapses on itself, several things might happen. One, it collapses in on itself and creates so much pressure, there's going to be an explosion, boom, nova, supernova. If there's so much gravitational pull, it's going to collapse in on itself, and there's not enough. And yes, there might be an explosion, but it's not enough to blow it back apart. Black hole. At least according to our theories. And it's amazing we come up with anything, considering we are here in the middle of an arm of a spiral galaxy, looking out at the universe, trying to draw conclusions from what we can see with our limited abilities. It boggles my mind. Anyway, black holes and the fact that our sun won't become a black hole. Questions?
So I still feel like you just moved that over to the right side and times it by 2 and
Yep.
but then that's still initial velocity squared. But then you
That's
just
speed.
said c squared.
Yeah, so if I just did that and I left it, so then I have, you're right, vi squared is equal to 2 big G mx over rx. All right. Remember, I can make anything a fraction by putting it over 1. So now I have two fractions equal to each other. And I can move stuff across the diagonal. I can flip rx and vi squared across the diagonal. Or, I guess, what I'm doing ultimately is multiplying both sides by rx divided by vi squared. But vi squared gets over here by dividing it, rx gets over here by multiplying it, and get that equation.
But I thought you said earlier that c is not velocity, initial velocity.
All right, so I guess back to your other question. given the way our current sun is, light is definitely escaping it. We can see, look outside and we see light. Matter of fact, there's a lot of radiation coming off the sun. So objects can leave the sun. The light is traveling at the speed of light, and so it's definitely traveling fast enough, but in theory, with the size of the sun, excuse me, with the size of the sun and the mass of the sun, smaller things can also leave. It's just very difficult to test that, because anything that we put close to the sun most likely would get burned up before it could actually launch. As the sun shrinks, assuming that the mass stays the same, as the sun shrinks, then I'm getting closer to the center. Because right now I'm roughly 6.4 million meters away from the center of the Earth. If the Earth shrunk in half, kept the same mass, I'm now closer to the center than I was before, greater gravitational pull. As was written over here, since R is on the bottom, R squared is on the bottom, as R gets smaller, you get a bigger fraction. Good so far?
Yeah.
So as it gets smaller, as there's a greater and greater gravitational pull, it requires more and more speed to actually escape it. So that's the escape speed for Earth. If the Earth shrank to half the radius, the escape speed would be around 44,000 meters per second. So the smaller, I'd have to rethink that. It's going to be something bigger. So the greater the gravitational pull, the harder it is for something to escape. So as the radius gets smaller, if we did a plot, because who doesn't love a graph? So VI versus radius. So as radius gets smaller, put that over here. So as R gets smaller, the escape speed increases. Or as the radius gets bigger, the escape speed gets smaller. Because if Earth were the size of Jupiter, I'm much farther away from the center. And so if we had a current mass size of Jupiter, we could, in fact, I suspect we could jump from top of buildings. It might end up in a Tesla thing. So if you accept the fact that if the Earth expanded, the gravitational pull would get smaller because you're getting farther from the center. And there are some people who do believe in the Earth expansion theory instead of plate tectonics. Conversely, if the Earth suddenly were shrinking, the gravitational pull would become greater because you're closer to the center. Center distance gets smaller. There's going to be at some point, because as the escape speed increases, at some point there's that maximum limit. There's the limit of the speed of light. So if we theoretically plotted R versus V, there is a point, the Schwarzschild radius, at which if the central object became smaller than that, even if you're traveling at the speed of light, you cannot escape. I don't know if I'm answering your question or not.
I think so. Maybe. Yeah, then C is the speed of light. Okay, I guess. Yeah. I guess.
Well, if you, in my mind, I answered the question that I heard, not necessarily the one that you asked. So we can always revisit this later, if need be. All right. Other questions at the moment? All right, time to bring it back down to Earth. The ski slope problem, and our nice ideal frictionless snow. We now have a non-conservative force in play, and we have to figure out how to deal with it. ski slope. A snowboarder, a skier, somebody who's gonna slide down the hill. The distance from here to here, we will make 50 meters. And what I want to know is how fast is the skier going down to the bottom. There's no friction. We'll represent that by, so let's say sliding, the kinetic friction is equal to 0. Coefficient of kinetic friction is equal to 0. We assume that the skier is sitting balanced at the very top and a gnat lands on his back. When the gnat lands on his back, it's enough to give him a slight push and he will start going down the hill. But the initial speed is close enough to 0. So first, force diagram, that's never going to go away. If we look at the forces, let's look at the forces when he is here. So to do a force diagram, when we draw that out separately here, what are all the forces acting on the skier?
Normal and weight.
Yep. So I have weight acting down, I have normal acting this way. Weight, conservative, non-conservative.
That's conservative.
Normal force?
Non-conservative.
Okay. So potentially we have this issue because if, so far we've dealt with conservation of energy, but that only works if we have only conservative forces in play. So if we go back to the formula of work, work is force times displacement, is a dot product. So when he's at this point on the ski slope, in which direction is he moving? In which direction will his displacement be at that point? I think you pointed in the right direction, Aaron. I couldn't quite tell. Yes. Which way is the normal force at this point? They are indeed perpendicular. So what is the dot product of perpendicular vectors? If you recall, dot products multiply parallel components. So if they're perpendicular, or if we go to the other definition, W equals magnitude of F, magnitude of delta S, times the cosine of the angle between them. If the angle between them is 90 degrees, what's the dot product? Anyone in here had, at least someone in here has that trig, right?
Mm-hmm.
Yeah, what's the cosine of 90 degrees?
1, I think.
With cosine of 90?
90. Sine is 1.
1.
0.
It is 0.
Okay.
If you think back to the unit circle, any point on here, if that angle is theta, radius is 1. This is cosine of theta, sine of theta, the x and the y. If I'm here at 90 degrees, my x value is 0.
Oh, I went straight to 0 degrees. That makes sense.
If two vectors are perpendicular to each other, the dot product is 0. Matter of fact, that's a test of perpendicularity. If you have the two vectors, find the dot product. If the dot product is 0, they're perpendicular. So since the normal force is perpendicular to the displacement, at any point in here, the displacement is always perpendicular. Even though the magnitude, even though the normal force changes direction constantly, but so does the displacement, they're always perpendicular to each other. So since the normal force is perpendicular to the displacement, the work non-conservative is equal to 0. So even though we have a non-conservative force, it is not doing any work. And since it is not doing any work, we have only conservative work being done, energy is still conserved. So my initial energy is equal to my final energy. And my initial energy, I have two types. I have kinetic plus potential. Here we go again. Everybody in unison. It's going to be a beautiful thing. What's the formula for kinetic energy?
1/2 m squared.
Not quite the chorus yet, but again, we'll get there. Plus, and the formula for potential energy?
Which one?
The one associated with our conservative force of weight.
MGH plus C.
So it's MGH initial. I'm not going to bother writing plus C. It's there. It's going to cancel out immediately. MT final squared plus MGH final. All right, what's equal to 0?
Max. Cancel as well.
Okay, not equal to 0, oh, right. But it'll cancel out, so we can divide everything by mass. It goes away. All right, what's equal to 0?
Initial force.
Let's, yes, but more specifically, the initial speed. All right, that is 0 because my initial speed is close enough to 0 for a physicist.
Final height.
Why?
At the very bottom, you know. Well, since they're going down the ramp, if we go all the way to the bottom, wouldn't that be just 0 meters? Since they're at ground level.
That's not the reason why.
We didn't say it's ending somewhere above the ground. Like that, it doesn't have a final height.
So